Okay, so as you are aware, you're more or less expected to be going through this stuff on your own with the general playlist, but also reading on your own. Don't forget that we actually have a book for this class on which all this other content is based, PowerPoints, videos, whatever. But uh, a quick couple mentions about these definitions before we get into our first quick check question. Force is a push or a pull, right? I mean, you feel it's something that you feel actually, something that you feel physiologically. Um, your nerves. Well, what do your nerves do? Your nerves sense some sort of like change because there's always electric current going through them, and anyway, it's very electric what we feel. Force acts on an object. Force pushes and pulls are applied to something. A lot of this is pretty clear. Yeah, we use the word exerted a lot. Force is exerted on an object. Um, that's certainly helpful. A couple of these pictures are good to keep in mind about an external agent. So force always has an external agent. So the agent, really external agent, is the thing that applies the force. So in this example, when you throw a ball, right, your hand is the agent. I want to take that a little bit further. So let me jump onto the whiteboard. Let me jump onto the full screen and do some annotations. Let's see, I got the right color. Good. Okay, so in this quarterback, right, we have the football, right? And so football is okay. So it'd be helpful to kind of organize this stuff. So obviously the ball feels a force to the left. So that's the force of the maybe QB on the ball. Okay. It's the force of the quarterback on the ball. Well, the ball is exerting the same type of force on the quarterback, but it's just in the opposite direction. And that's important because, right, it's the same size. So that's the force of the ball on the quarterback. Much gone into much more detail in chapter 7, but the reason I bring it up is that you can see here that the quarterback has, see, his right foot planted on the ground, right? And we plant our right foot on the ground to keep us from slipping, right? I mean, it makes sense, but let's think about it in terms of forces. Because what do you do when you plant your foot? Another good example is bowling, right? Last time you've been bowling, you plant your, what do? You plant your non-dominant foot and as you throw the ball, right? And these balls are like what, 8, 10, 12 pounds. I mean, um, these balls that are solid kilograms. I mean, around 5 kilogram massive object. And so you're accelerating a massive object. And so you have to push backwards on the floor. And so this would be the force of the quarterback on the floor, which the floor then in turn has to push it forward. So this would be the force of the, well, whatever you want to call it, the force of the floor on the quarterback. And so you have to keep in mind that forces are not isolated, right? This slide is just talking about the force that the ball feels, but it's part of a big system of forces of different interacting objects, right? The surface, the quarterback, the ball, even in some small sense, the air, the earth is pulling down on the quarterback is pulling up on the earth. Forces are not isolated and they occur in pairs, and more realistically, everyday systems, there's several pairs with many different interacting objects. Okay, I mean, because these two forces, the force of the ball on the quarterback and the force of the floor on the quarterback, have to, in a sense, balance to keep the quarterback from sliding. Right? Imagine if you were, doing this on like ice, right? Which isn't that hard to come by right now. If you do this on an icy surface, you're gonna, get flung backwards because there's a single force causing you to go backwards. This one right here, actually. And so there's, identifying agents, right? You've got the quarterback as the agent exerting the force on the ball, right? But the ball is the agent exerting a force on the quarterback, and then the surface is the agent exerting a force on the quarterback, but the quarterback is also an agent exerting a force on the floor, on the surface. And it can't be a slick surface. It's got to have friction. Got to be a rough surface so that there's friction. So, and then also this cue ball example down here. I mean, we the slides are talking about, okay, so this is the cue ball feels a force from the stick, right? Propelling it forward, actually causing it to accelerate forward, but the cue feels a backwards force as well. And the person feels a force as well from the cue stick. So there's all these different forces that are in play, no pun intended, when an object has a force applied on it. So again, I don't want to go in too much lecture, just perspective for our problems that are helpful. So we got contact and long range forces. Contact forces are really the only ones we deal with in physics 1. There's only one long range force that we're using in this class, that's gravity, officially, the forces that we use. What is contact? Well, Vsauce, Michael here, he's from Kansas actually, has a great video on what is touch. What does it mean for two objects to actually be touching? And the way he sort of defines it is that the outer electrons from the baseball are close enough to the outer electrons of the bat that those electrons start to push against each other measurably. When they're not in contact, the repulsive force is essentially zero. And when you get to a certain distance, then the force just blows up, becomes infinite, and you can't really tunnel the baseball. You can't like tunnel through the bat. And so the force becomes not infinite, but practically. So any sort of contact would have an electric, really like an electric genesis. Of course, gravity objects don't need to be in contact with one another to feel these pulls, right? That's why the moon orbits the Earth the way it does. Happy late Lunar New Year. And so, contact force is the only ones we're going to be really dealing with besides gravity. Contact doesn't necessarily mean a single point of contact, actually. Anything that moves through the air feels a contact force really everywhere on the surface of that object. Same thing if you imagine like a submarine moving through the ocean, right? To go up and to go down, to move, laterally in any direction, to rotate. There's all these drag forces from the water in contact with the, outer edge of the sub everywhere. So contact isn't necessarily a single point. For most of our examples, it'll be clear. I mean, even an object sitting on a table, really the box is in contact with the object in a cross-sectional area. But most of these contacts that spread out over an area, we're going to model as just being a particle or being as a single point, which leads us, I believe, to our first quick check question. Yeah, there's our first quick check question. In this example, obviously this velocity is going to increase as the ball takes a parabolic trajectory. The velocity is going to increase, and maybe you pass this little edge here, and the ball will just keep getting velocity will just keep getting larger and larger. And the point of this chapter is, how do we resolve that with our intuition versus what a force actually is, how a force is actually defined? It's surprising. Okay, yeah, I see. So pretty much everybody thinks that the weight of the ball is acting on it, which is good. Gravity's pulling down on it. But what about this horizontal part? Well, what does a force do? Right, what a force does is increase the velocity. It changes the motion. Is the motion of this thing changing? Well, sure, but only in the y direction. The motion is not changing in the x direction. Remember, the velocity v sub x is the same in all these cases. And forces only change the part of the motion in the direction in which they act, because forces are vectors. I think that was in the slides earlier. That's one example. Well, another reason is that forces are often different from what you feel. I mean, when do you feel being pushed forward when you're driving 40 miles an hour on the road? Well, no, besides the little bumps and, grooves that you encounter in the road. Um, when you're in a plane, right? When after you take out after you've reached cruising speed, you're going several hundred miles an hour. Do you feel that? Do you feel a force pushing you to maintain that several hundred miles an hour force? And the answer is no. Same thing with a train or whatever. You don't ever feel motion. And so, choice C, for instance, a force whose direction changes as the direction of motion changes, that's not what you're feeling. Actually, what you would feel if you were this ball, or if you were like falling down the slide, and after you've left the slide, you would feel pushed upward. You would feel like a pull upward, strangely enough. Right? And that's because we feel some sort of magic pull that's always opposite our actual acceleration. So we're not accelerating upward, we're actually accelerating downward. And so for choices D and E, we're just mixing up force and inertia. Okay, just an object has inertia, which means it'll maintain its motion no matter what's acting on it. And I'll admit that that's different from our everyday experience. Our everyday experience is, well, you kick a soccer ball, that's eventually going to come to rest. You have to step on the gas to keep your car going 40 miles an hour on the road, right? Those types of things include these dissipative forces like air resistance and friction. So technically the answer is A. It's just the weight of the ball. Technically, the book doesn't even use weight in that context. It's the force of gravity, but okay, we'll just stick with that. So the answer is A. And for folks choosing D and E, even if folks thought C, where there's no force keeping an object moving. Once an object's moving, it's moving. That's what inertia means. Good, very good. Okay, well, let's move on to the next stuff, which is a brief sort of summary, one of these tactics boxes, I think, on how to draw force vectors. And I'll just use this in the context of an example. So tactics box, what is it, 5.1, drawing force vectors. Certainly helpful to see this stuff, but you have to really see an example to show why we do this. So what are all these different bullet points here? Model the object as a particle, draw the tail of all the objects at the same point on the particle, draw the force vector as an arrow, pushing it away from the particle in the proper direction. What is the last one? Give the vector, because it is a vector, give the vector an appropriate label. So label the vector, it has to come from the, let me do an example of these types of issues that we can encounter when we're doing these things. Because it's one thing to read the tactics boxes, it's another thing to see it in a context. So let's say you're pushing a heavy box across a carpet. Whoa, that was cool, but not what I meant to do. So what I do in my drawings, I draw straight lines, and these squigglies represent rough surfaces. It's supposed to be a relatively straight line. Okay. Let's say, so you're pushing a box to the right. What are all the forces acting on it? Okay, a lot of us will say, well, gravity, and then normal, and then friction. Here's what we're trying to avoid when we identify forces. So it's helpful to identify them, but drawing them out, there's a good way to do it, and then there's a way that is makes it really challenging. So if I just drew the push, say if I drew the push over here, I call that, didn't label it, gravity, let's say acts right here, let's say I call gravity G, let's say, okay, the normal force, let's say the normal force is like right here. What am I going to call that? Maybe capital N. And then friction acts backwards. Maybe call that F. I mean, you can get the sense that this type of drawing is going to lead to confusion because ultimately you want to add these vectors together to get some result. And that result will be really important. So instead of drawing it this way, I think I did pretty much every bullet point that the thing said not to do. First thing is model the object as a particle. I'll even go a step further, kind of look ahead and say, okay, well, let's draw a free body diagram. Free body diagram has coordinate system, reasonable, I'm redrawing, has a reasonable coordinate system, right? So X and Y, use a standard X and Y unless we're on an incline, okay? And we're going to draw the particle. We're going to model the box as a particle. It's going to be centered at the origin of this coordinate system. Then, so first of all, this vector on the left isn't even labeled. So maybe label it capital P. Now you take all these vectors, you have to start them at the origin of this coordinate system, which technically this isn't position X and Y. Technically it's the F sub X and F sub Y, but that's fine. So now if we take all the vectors and plop them right in the center, you get a much more coherent picture. So the force, that push vector, I'll try and distinguish between vectors and axes. Change the weight of my pen. There we go. Okay, so I changed the weight of my pen, so hopefully there's not, I can do red anyway. So this will be the push. And don't draw arrows like on the coordinate axes. That just causes more confusion. That's one thing that the book doesn't say. But the book doesn't do that. The book doesn't draw arrows in the direction of the coordinate system. So that would be the push. So capital P with a vector. And then, so another thing that's wrong about this example is that on the left is that they use G for gravity. We don't use G for gravity. It's tempting because, well, gravity starts with G, and this is a G. But little g is not gravity. Little g is our acceleration due to free fall. Well, how is there g even though there's not acceleration in free fall? Well, that's where we get into what the gravity force is. So we label gravity as F with a capital G subscript. That's our label for now. Later in chapter 6, we'll find out that the magnitude of this gravitational force is proportional to the mass times the free fall constant. And depending on folks' comfort level, we may use one or the other. Normal force. What is normal force? Well, we've heard about this thing called the normal force. What is it? Several examples to think of. When you're sitting on a bed or when you sleep on a bed, right? The mattress is obviously sinking. And so the springs or the foam or whatever on the mattress is kind of pushing you upward, but it's sagging, right? So there's kind of that sag when you're on it. Same thing with the trampoline, right? Trampoline sags while you're jumping on it ever so slightly. It's hard to picture that microscopically, but that's what happened. I remember one semester I had a long meter stick, and I more or less had the student push down on it with a force. I'm going to switch pins here in a second. What happens to the meter stick? Well, what happens to a string when you pluck it? What happens to a drum when you hit it? What happens to you know, something when you hit it very hard. Well, there's a brief impact followed by some compression and then some wobbling. Right, so you push it down, the string staying where it's at will dip ever so slightly, and then it'll wobble back and forth. We'll learn about the rates and stuff of the wobbling and the frequencies of the vibrations in chapters 17. But for now, the thing's going to wobble back and forth until it settles back in its initial flat state. And that's the same thing if you push hard against a wall that's sagging in microscopically, you let go, right? There's going to be microscopic vibrations in the wall that will return the wall to its flat state. It's very, very interesting, and it's not something that we would ever think about because, to the naked eye, it just looks flat. But in fact, that's what's happening. So the normal force, that's what the normal force is. We actually denote it with a lowercase n in this textbook, not a capital N. And we also need the vector caps. And so let's say it's going to point up, and it happens to equal the gravitational force in this example. We'll talk about why later. And then the last one is friction, right? Anytime we're on a rough surface. So yeah, again, on this left drawing, we would draw the friction kind of like on the edge there, but really it's acting everywhere on this surface. And so again, model the particle or model the object as a particle, and we're going to dump it backwards. So that's going to be, we use lowercase f for friction. That way we don't confuse it with force. Lowercase f, now that's a K subscript. And this, part of your physics education, it's the first time that you'll see the letter K in this class. And it's probably the letter that denotes the most stuff in all of physics in so many different settings. So it'll be fun to joke around about that. So in looking at this thing on the right, you see that all the forces are added together and they come from that single point, and we call this a free body diagram. Much more easier to work with than this awkward drawing on the left. And really that's what this tactics box is trying to argue, is that don't draw all the forces in all these different spots. Equally bad would be like drawing the free body diagram and having that push still be on the right side, right? So you have F there, and then what is that going to do? Friction's going to go back. I mean, this is still a confusing drawing. So that's why you have them all start from the same point. Line up all the tails. Think about them like quills on a porcupine. They're all starting from the same spot. And we have them all labeled. The only thing that we're missing in this free body diagram is something we haven't even introduced yet, which is the concept of F net. So F net is the vector sum of all the forces. Older textbooks call it the resultant force, which it's the same, it's the same word, resultant or net force. We typically use net these days. So it's the graphical, you can add this up graphically, right? It would be the tension, not the tension, the push force plus the gravity force. Notice how even though these act in different directions, we still add them up graphically. Let's have some K. And you can do that activity graphically as well. In this context, doesn't matter which one you start with. If we start with push, okay, we'll start P. So this will be the starting point, far left edge of push, and then maybe what are we going to add? Add gravity? Well, then let's add gravity. Sorry. We're doing tip to tail. And then add normal force next. Okay. If we add the normal force next with the same tip to tail, it's going to be kind of up. And then the friction force points backwards. Same tip to tail method. And so this vector right here is what we call F net. That is the vector resultant. you can also add it up by doing it numerically with components, which is more standard for a lot of the problems. And so FNet, it's not, it doesn't have an agent, right? The push was done by the person, right? The normal force was exerted on the box by the floor. Friction was exerted by the agent of the floor, right? Agent of the gravity force is obviously the entirety of the Earth, technically the entirety of the universe, but Earth is really the only thing in the universe that exerts a moderate gravity force. Moving on. But this net force is not caused by a net agent. It's just the mathematical result. And so since it's not caused by an agent, we put it off to the side, wherever it's convenient. So FNet off to, I tell folks to put FNet off to the side. And this right here is a complete free body diagram. Great. I would get very comfortable drawing these. It has everything that a free body diagram needs. And I know the tactics box was just talking about simple force vectors, but oops, sorry, I'm all over the place. This is what you want to aim towards in this chapter. You want to aim towards drawing all this stuff in a single spot. Now, identifying the forces might take some time, admittedly, but that's our goal. Okay? Don't neglect FNet, because there are problems down the road where neglecting FNet will give you the wrong answer. It's always a shame. Back when I hand grade quizzes, people get the wrong answer because they don't write FNet. So I implore you to write FNet down. So this is an example of a free body diagram that I want you to be able to write out the best you can. Right. Okay, so with that in mind, I want us to I want to quote Newton's laws in a form that I think is helpful. Not necessarily one that you may have seen before, but it's also good practice with some other things like logic and vectors, actually. Okay, so what's Newton's first law? It's always relating acceleration to force. Okay, so really quickly, what's acceleration? We've seen it in many different contexts, right? Acceleration is what causes an object's motion to change. Now that can mean lots of different things. That could mean, increasing speed, right? We can have these vectors that are getting bigger. Increasing speed, it could be decreasing speed, right? From backwards acceleration, right? And remember, when you decrease speed, you're accelerating backwards, right? So when you approach the ground floor of that elevator, or when you approach the ground floor of that building, you're accelerating upwards. So you're accelerating upwards even though you're moving downwards. So when you're slowing down, you're accelerating opposite your motion. That doesn't necessarily make the acceleration positive, right? What makes the acceleration positive is the choice coordinate system. And then also, like in projectile motion, we saw that like one of the homework problems of throwing an Olympic shot put. If you have an acceleration that points in a single direction, then by and large, your motion in the direction parallel to that is unaffected, or sorry, perpendicular to that is unaffected. The x component of the velocity is unchanged, while the downward acceleration causes the y component to increase or decrease accordingly. So, okay, that's a good picture. All right, so the horizontal part always stays the same. The vertical part is what either slows to rest and then turns around, or just increases speed based on acceleration. And then, of course, for circular motion, well, you're always accelerating towards the center in circular motion, unless you're speeding up or slowing down, in which case you can accelerate tangentially, right? You can accelerate tangentially as well as centripetally. Okay, so all these different types of acceleration, I'm certainly not going to go all of those in detail because I want us to be able to appreciate first law. I'll just have to read. I'm just going to read. Oh, but I'll just undo. Okay. Okay. So what does Newton's first law say? If you have a zero acceleration, and this is a vector, that is equivalent to the F net being zero. All the forces acting on an object happen to add to zero, and that's the same thing as zero acceleration. Sometimes we call this the law of inertia. This is almost a definition of what inertia is. And, inertia means that an object, if it's not accelerating, there's no net force on it. You can still have forces acting on it, but they all balance. They all cancel out. What's interesting is the second law. And the second law is, well, let's start by seeing if it's just the negation of the first law. What's the negation of this logical statement here? Well, it just says that if the acceleration is non-zero, I have to make sure I get that right, then that's equivalent to saying that F net is non-zero. But if you think about it for a second, Newton's second law says more than this. Okay, because if one thing zero makes the other thing zero, then one thing non-zero making the other thing non-zero doesn't specify how they're related. It just says that they're non-zero. So technically, if the second law was just this logical negation, then you could have things like this. You could have a net force to the left causing an acceleration to the right, or up, or whatever. And yet that's never been observed. Again, these are statements that are based on, empirical observations, and we never observed that an object with a net force to the left feels or accelerates up and to the right. We never observed that. Well, so it's got more to, the second law has more to say than just negating the first one. And here's the second pair of statements that I think might be helpful, because oftentimes more theories are presented in this way. Here's something else to consider. This is something that greatly restricts the possibility of how these are related. And I'm going to say that the cross product of F net and acceleration is zero. What does that tell you? Well, if the cross product between two vectors is zero, that means that they either have to be in the same direction or in the anti-direction. That's the only way that the two cross products can be zero. So how do we eliminate this bottom possibility? Well, require that their dot product, I guess these have to be real vectors, require the dot product be greater than zero. So when the dot product of two objects is positive and the cross product is zero, that requires that they are co-parallel in the way that you would expect them to be. So the Newton's second law says more than that, actually. But it goes further than that, actually, because once again, if you just knew that they were parallel, or if you just knew that they were parallel in the same direction, that begs the question, well, how are they, what's the constant relating them to, or what is the numerical value that they're related to? Because if two vectors are parallel, that means they're related to each other by a scalar multiple. And that's the final thing that we get, is that we get this constant of proportionality between force and acceleration. So that constant of proportionality ends up being a true constant. This constant ends up being really a property of the object's inertia. What are some things that experimentally that this constant does not depend on? It does not depend on, I'll just call it, give it a name, m, calling it a mass. What are some things that it does not depend on? It does not depend on velocity. At least not near the speed of light, or near the speed of light it changes, but it does not depend on time in these examples. It does not depend on position. You know, it doesn't even depend on temperature or any other pressure, quantity, or any other thing that you could think of. It's a true intrinsic property of the object. What is mass? You know, that's a pretty deep question, and we don't have enough time to talk about it right now. But needless to say that Newton's second law says a whole lot more than just negating the first law. This equation, technically, I don't even write it down. Technically, this book also offers something called the Newton's zeroth law. I'll even spell it out. Newton's zeroth law of motion. We in physics, we love to do stuff like this, just like computer scientists. They like to make little acronyms. What does Newton's zeroth law say? That these things are happening in equal times, that the acceleration at a specific time, you know, is due, well, we know that mass doesn't change with time, but that the acceleration at an instant in time is due to the net force at the instant in time. And that usually doesn't cause much problems, but it definitely resolves this zeroth law, which is really not so much a law as a result of physics education research. It really says that, like, it resolves situations such as when you throw a ball up into the air, right? After it's left contact, the only force is gravity. The force of the throw doesn't persist after it's left contact with your hand. That is, forces from the past can't expect accelerations from the future. That sounds kind of silly, but you'd be surprised what our brains will do when we're reasoning about these situations. Now, of course, there's a third law, and there's an entire chapter devoted to that one because that's a little bit more confusing. And so what we'll do in the next lecture is just continue and try and reason through as many different situations as we can involving forces. There's a few more things to say about chapter 5, but we're really ready to start handling more everyday situations from the context of forces.